Hello, so in this video we're going to be looking at how we can solve a particular type of example using the logistic model, including including a harvesting term. Okay, so here's the question. A forest can support a maximum herd of 500 deer, whose population has a linear growth rate of 20% per year. Okay, so already, just in those first couple of lines, a forest can support a maximum herd. So already we're thinking, okay, we've got a carrying capacity included. Okay, so it is limited. Now, so therefore it will be a logistic growth model rather than just an exponential model. Okay, 500 deaths, that's a population. That's our carrying capacity, because that's the maximum amount that we can support. So that's 500 is our carrying capacity. Okay, it's a maximum population, whose population has a linear growth rate of 20% per year. So that's our growth rate. Okay, first part of the question asks, what is the maximum number of deer that can be killed each year without eventually driving the population to extinction? So basically we're saying, well, okay, what is the maximum amount that we can harvest what's the maximum harvesting term that we can have without causing instability and without causing an extinction to the population? Okay, so what is H effectively? Second part of the question asks, how many deer can be killed by hunting each year to maintain the herd size at 300? So now we're including an extra kind of element involved, in that we're basically saying, well, okay, what do we have to do? So how many do we kill in order to keep it at 300? So, you know, the carrying capacity is 500. How many are we going to have to kill in order to control the population at 300? So that's a bit like a cull, right? And what is the minimum initial herd size that can commit this? So basically we have to then consider, you know, what is the initial population that we have to start off with. So, yeah, okay, let's have a look at that. And then part C asks, for the hunting rate found in B, so the hunting rate, we find hunting rate in here. Draw a rough sketch of the population size changes with time for different choices of population size. Okay, so we'll come on to that thing. So first of all, we're going to ask ourselves, what is the maximum number of deer that can be killed without driving the population to extinction? So in other words, what is H? Let's first of all extract the irrelevant information. So we've got K equals 500 and R equals 20%. So we've got K equals 500 and R equals 20%, which I'm going to write as 0.2. Okay, and we're going to be using a logistic growth model, so dn by dt equals Rn times 1 minus n on K, and then minus a harvesting term, so minus H on the end there. Okay, so first things first, we're going to have to try and solve this model using these relevant parameters to find out what H is. Okay, just like we did in the kind of general example, the video before. So here we go. So let's just put in all the first part for part A. We're just going to put in all of the values. So dn by dt equals R, which is 0.2. Actually, I'm going to write 0.2 as a fifth. Just going to make things so much easier rather than dealing with a decimal each time. So R times n, lots of 1 minus n on K, which is 500. K minus some harvesting term. So basically now we've got to try and solve this, and we're going to solve it using phase portraits. Okay, using phase portraits. So in other words, we're going to have to find first of all the equilibrium point. So that's going to be when this is equal to 0. Okay, so we're basically setting 1/5 of n lots of 1 minus n on 500 minus h equals 0. Okay, so let's expand this thing out. So we end up with 1/5 of h minus n on 2,500. Yep. Sorry, that's not n. That's not h. That's n there. 1/5 of n minus 1/5 of n on 500. So that becomes n on 2,500. Then minus h equals 0. So that's n squared, isn't it? What am I doing? Yeah, because it's n times n. Yeah, that's better. So yeah, let's just expanding this bracket out. Okay, let's do a little bit more work with this to kind of get rid of the fractions, hopefully. So let's multiply through by 2,500. Multiply through by 2,500. So minus 2,500. Let's get rid of this negative as well. So let's make it n squared. Okay, this is going to become minus 500n, because it's going to be 2,500 divided 5, which is 500. Okay, plus 2,500h equals 0. Okay, so now it's just a case of solving that, and we're going to solve it using the quadratic formula. So let's have a look at what the equilibrium points are going to be doing. So our equilibrium points are going to be minus b, so minus 500, minus 500, so that's going to become 500, plus or minus the square root of b squared, so 500 squared is going to become 250,000, yep, 2,500, minus 4 times a times c, so minus 4 times 1 times this 2,500, so minus 10,000, yep, all over 2 times a, so all over 2. Let's do a little bit of simplification now. This 2,500 minus 10,000, can we do anything with that? Sorry, I've made a mistake here. There should be an h in here, shouldn't there? Because it's 4 times c. Well, this is all c now. Okay, so it's 4 times 1 times 2,500h. Yep. Okay, so this is how we get this. Well, I'm going to actually do a little bit of work with this. I'm going to actually take out 10,000 out of this, so I end up with 500 plus or minus 10,000. Square root of 10,000, lots of 250. No, no, it's going to be 25, isn't it? 25 minus h. Yeah, because I've just taken 10,000 out of 2,500, so it's 25. Yep. Okay. And that's all over 2 as well. All over 2. I could simplify it down a little bit further, but now I've got to basically consider this discriminant here. So the discriminant, oops, where are we going? There we go. The discriminant, which I'm going to denote by capital letter delta, is going to be the thing inside the square root. So 10,000, lots of 25 minus h. Okay, and I've basically got to consider 3 different cases. So, in other words, when it's greater than 0, okay, so when the discriminant is greater than 0, that implies that 10,000, lots of 25 minus h is greater than 0. Okay, when it's equal to 0, okay, and when it's less than 0, so it's the same kind of thing, which is going on. So basically, I'm just considering all these different options. So 10,000. I'll pause the video and write. Okay, so there we go. Okay, cool. Okay, and this has the case when, let's have a look. So this is the case when we have 2 equal roots, E1 and E2. This is the case when we only have 1 equal root, so E1 equals E2. Okay, and this is the case where we have no equal roots, so no roots, or no equilibrium points in this case. Okay, so let's draw all the different examples again. So let's just draw it out for you. Okay, and remember we've got a negative quadratic going on. Where are we? We are here. Okay, when we expand this out, we'll basically end up with a negative quadratic. Okay, you can hopefully see that that's a negative quadratic there. Okay, because it's the highest power, and the coefficient associated with the highest power is a negative. Okay, so it will be a negative if you expand it out, so therefore we're looking at a negative quadratic. The first case is when the discriminant is greater than 0. Second case when the discriminant is equal to 0, and the discriminant is less than 0. So you saw all this in the last video, which is why I'm going through it quite quickly. So you end up with 2 equal roots here, E1 and E2. Okay, this is the case where we've only got 1 equal root, so in other words we're here. So this is just 1 equal root, let's call it E. And this is where there's no equal roots going on. Okay, and then when we plot the phase portraits, we get this kind of thing happening. So I'll start from left. So here's our equilibrium points, E1, E2, E1, E2. Okay, and here we've got positive rate of change, moving to the right. Here we've got negative, and here we've got negative, which moving to the left in both cases. Okay, so E2 is our stable equilibrium point in this case. Here, both sides of the equilibrium point are negative, so therefore both sides of the equilibrium point are negative. Right above. Both sides of the equilibrium point are negative, which means it's unstable because we move in from one side, but we carry on moving past it, so it's unstable. And here we've always got, basically, the population has no equilibrium points, and it's always driven to extinction. Okay, so it's quite a grim situation for that one. Okay, so basically what we're asking is what is our maximum H, okay? Okay, so in other words, the only viable equilibrium point is going to be here at E2, okay? And this was when the discriminant, was what was it? It was greater than 0, yeah? It's greater than 0, so that happened when the discriminant was greater than 0, okay? Discriminant was greater than 0. What was our discriminant again? Let's find our discriminant again. It was 10,000 times 25 minus h. So 10,000 times 25 minus h was greater than 0. Okay, so let's just do a little bit of rearranging. We end up with 25 minus h. We've just divided through by 10,000. It's got to be greater than 0. Okay, which implies that 25 has got to be greater than h, just by moving on the other side. So that basically implies that, just right around the other way, h has got to be less than 25. So basically the absolute maximum that the population has got to be is there. Okay, it's got to be less than or equal to 25. Because, you know, basically the hunting population has got to be less than 25. So the absolute maximum that it can be is 25. Okay, because if we can consider this case up here, where are we? When it is this case up here, where there's, you know, this is kind of, if you like, a limiting case, which you said in real life that will never happen. Okay, it can't be equal to 25, so strictly speaking, it's got to be less than 25. Okay, so actually, yeah, let's just keep that as less than 25. No, I'll keep that as less than or equal to 25, just purely because what we're asking in the question is what is the maximum? What is the maximum hunting rate? If I just pull the question up again, what is the maximum number of deer that can be killed each year without eventually driving the population to extinction? So that actually the maximum number has got to be, you know, 24.99999999 deer. Well, obviously you can't have 0.99999 recurring, you know, bit of a deer. It has to be then 25. Okay, so the maximum number of deer, which is so the max is h equals 25, because, you know, what happens if h is greater than 25? Well, look, you can see it from this example. We end up with you know, an unstable. It's always driven to extinction, you know, from that phase portrait. So in other words, when discriminant is greater than 0, so we've got 10,000 lots of 25 minus h. Okay, it's greater than 0, then that implies just divide through by 10,000. Okay, we end up with 25 minus h is greater than 0. So that implies that 25 has got to be greater than h. Have I got that right? No, sorry, that's less than. Ha. That's less than. Sorry to confuse you. That is less than. So I'm just considering this case up here. So discriminant is less than 0. So discriminant is less than 0. Okay, so therefore I've got this going on. So the discriminant, which is 10,025 minus h, has got to be less than 0. So therefore 25 minus h, just by divided through by 10,000, has got to be less than 0, which then implies that h has got to be greater than 25. And if that case, then the population is always driven to extinction, so unstable. So in other words, the absolute maximum that it can be, is h equals 25. Okay, h equals 25. So now the next part of the question, what was the next part of the question? Part B. How many deer can be killed by hunting each year in order to maintain the herd size at 300? So in other words, we want the herd size being 300. And note the second part of the question, and what is the minimum initial herd size that can permit this? Okay, so let's have a look. Oh yeah, notice as well, this should have come as a proviso. The maximum is h equals 25, providing the herd size is greater than E1. So in other words, providing the initial herd size is greater than E1. We talked about that in our last video, because if N0 fell over here, then we'd move away from the equilibrium point, so it'd be unstable. So it basically needs to be the right of E1 in order for it to always converge towards E2. Okay, because even if it's to the right of E2 as well, it will still converge to E2. Okay. So providing N0 is big enough, basically. So the second part of the question, we need to maintain the population at 300. So basically, we need to maintain a population. This is part B now. We need to maintain the population at 300. So N equals 300. Okay. So therefore, we need to basically ensure that the equilibrium point. In order for that to happen, we need to basically make sure that the equilibrium point E2, this equilibrium point here, needs to be equal to 300. Okay, so basically what we need to do is because, you know, we're in control of the system, and we need to basically make sure that whatever hunting rate we use a hunting rate in such a way that, you know, obviously we need to consider a large enough population such that it will always converge to E2. So we're considering this case, because in all other directions, in all other cases with different hunting rates, it always diverges away from, you know, the equilibrium point, or it diverges to extinction. So it's unstable in both of these cases, but basically we're looking at E2 now, and we need to basically choose E2 to be 300 because that's the value that of the herd size that we want to converge towards. So E2 basically needs to be equal to 300. So what is E2? Well, E2, if you remember up here, where did I find E2? E2 is the negative of this. Well, actually, no, I didn't really write this out, did I? So basically, E1 is I've defined E1 to be the lower value. Okay, so that will obviously correspond to the negative root, and E2 I've defined to be the higher value, because if you look, it just lies higher along the n-axis, so it's got higher value, okay, to the right along the n-axis, so therefore it's got higher value. So E2 is the one with the higher value, so therefore it's the one with the positive root, because fairly obviously if you add something, 3 plus 2 is bigger than 3 minus 2. Okay, so E1 is the one with the negative square root, but E2, which is the one which you're interested in, is the one with the positive square root. So in other words, 500 plus square root of 10,000, lots of 25 minus h, all over 2. Okay, so that's what E2 is equal to. So let me just write it out again down here. Okay, so we've got E2 written out down here now. So basically what we're going to do is just fiddle around with this and see what we can do. So basically we need to make this, we need to choose a value for h that makes that equal to 300. Okay, so first things first, let's take out, well, 500 over 2 is going to be 250. Okay, so then we've got plus a half, effectively, of 10,000. Lots of 25 minus h. Well, this is just surds, right? This is just one thing multiplied by another. So I can split the square root up into two things. So I can say the square root of 10,000 times the square root of 25 minus h. All right. What's the square root of 10,000? Well, it's 250 plus square root of 10,000. That's 100, isn't it? So it's 100 over 2 times square root of 25 minus h. Okay, square root of 25 minus h. So 100 over 2 is 50. This is 50 times that now. Okay. Okay, so we effectively need to, so this is equal to 300, right? So we effectively just need to rearrange this to find out what h is. So let's do, first of all, take the 250 on the other side. So this is 300 minus 250 now. So 300 minus 250, which of course is 50. Okay, so we've got 50 is equal to 50 lots of 25 minus h. Okay, let's divide through by 50. Divide through by 50, so 50 over 50 is 1. Okay, so therefore if we just now say 1 squared is equal to h minus 25, sorry, 25 minus h. Okay, so 25 minus h equals 1. Okay, so that then implies that h has got to be equal to 24, right? 24, because 25 minus what equals 1? Well, it's got to be 24. So that is basically the hunting rate that is needed in order for the population to be kept at 300. So that's just algebra. That's just algebra, right? Nice and easy algebra. The second part of the population is what initial population size do we need? Well, we basically need the initial population size. Let's go back up to our diagram. Let's find it. There's our population. Okay, get rid of these arrows here. We basically need for the population size to be bigger than E1, right? Because if it's bigger than E1, then it will always converge to E2, which is 300 in this example. So our population size is, our equilibrium population is 300, as long as we choose a population, hunting term of 24. Okay, but if it's less than E1, then therefore, look what happens. We move away from E1 and we actually move to extinction. So basically the condition is that N0 has to lie to the right of E1. So N0 has to lie to the right, so it has to be bigger than E1. Well, what was E1? What was E1? Well, it was the one with the negative root, wasn't it? So it was 500 minus, this is going to be 100, or 10,000, sorry, 10,000 lots of 25 minus h, okay, over 2. I'm just literally getting that from, where's our equilibrium? Here. Okay, so E1 is the negative square root, E2 is the positive square root, basically. Okay, right, so I'm just literally taking that there. Okay, let's again do a little bit of rearranging. So what is E1 going to be? Because if we can find out what E1 is going to be, then N0's just got to be bigger than that value. N0's just got to be bigger than that value. So let's do a little bit of work. So this is 250 minus, this is 100 over 2, lots of 20 square root of 25 minus h. Okay, so 100 over 2 is going to be 50. Okay, so we now know that h has got to be 24. We worked it out up here that h has got to be 24. So therefore we've got 25 minus 24. 25 minus 24, which is 1. So what's the square root of 1? Well, it's going to be 1. Okay, so this is now just 250 minus 50. So this is 200. Right, so n0 has got to be greater than 200. So n0 has got to be greater than 200. So the minimum population size is got to be 200, or initial population has got to be 200. Okay, that's the absolute, or sorry, well, just bigger than 200. So the absolute minimum has got to be 200. Okay, now let's look at the third part of the question, part C. It's a long way up now. So for the hunting rate found in B, which is 24, so h equals 24, draw a rough sketch of how the population size changes with time for different choices of population size. So effectively now what we're doing is we're going to try and solve the ODE, okay, and we're going to draw kind of a plot which is going to dictate that. But if you look, we've already solved the ODE just purely by phase portraits. So using these phase portraits, okay, so in other words, we know what E1 and E2 are going to be, and basically for differing size of populations, we need to basically just take into account all of these different things that can happen with our graph. So basically, okay, so let's draw it on. So E1, so let's write out the values of E1. E1 was 300. Sorry, that's 2. E2 was 300. E1 was 200. Yep, so E1 was 200. We worked that out there. Or we worked it out here even. So E1 is 200 and E2 was 300. We worked that out here. Okay, so E1 is equal to 300. Okay, so basically we say that using our population, you know, because it was asked to use our hunting or harvesting size, so 24. So when h equals 24, this is what we get. We get E2 equals 300 and E1 equals 200. So that's kind of the first thing we say. And here's the plot. Here's the plots, okay? So basically we plot these on. We plot n against t. That's what we're asked to do. So n against t. We plot on 300. We plot on 200. And we just look at our phase portraits to see what we need to do for each case. Okay, so basically for here we need to move away. We need to move away from E1. So just below E1 effectively, we need to move away from E1, and then in all other cases we need to converge towards E2, so we need to converge towards 300. So let's draw these on. Okay, so let's draw our lines on like that, so it's 200. So basically we need to converge towards, converge towards 300, and here we need to converge towards 300, and here we need to move away from 200 towards 0. Okay, we don't know we don't actually know when it's going to reach 0, so we kind of just draw it as an asymptote like that. Okay. Now, what's going to happen for different values of, what was the different values of? For different choices of population size. So what is initial different choice of population size going to affect it? Well, as long as our initial population size is bigger than 200, so in other words, as long as it's above 200, so as long as we're falling in this region, we're always going to get these same graphs which we're drawing in here. In this kind of region here, we're always going to get the same kind of graphs. The population size is just going to affect this region down here. Okay, it's just going to affect the pattern down here. So in other words, this population size is still going to go to 0, but it'll just start at a different value. Okay, it's following exactly the same shape, but it's just going to start at a different value. Yep. So that's all it's basically asking us to do. Okay, so that's just an example, nice example of